So the purpose of this short video on electrochemistry for general chemistry students is to really drive home the link, so to compare and contrast the link between voltaic cells in terms of their change in potential energy and electrolytic cells in terms of their change in potential energy. So recall that by definition a voltaic cell, when you measure the voltage across the electrodes, has a positive voltage, and by definition an electrolytic cell, when you measure the voltage across the electrodes, has a negative voltage. If we take our electrodes and we revert back to a simplified representation that we've seen in a previous video, where we've essentially got two electrodes, we have the anode, which for a voltaic cell is negatively charged, and a cathode, which for a voltaic cell is positively charged. And we can see, because of the charging, we have, in this oversimplified illustration, we have an electric field that's flowing from the positive electrode to the negative electrode. And we'll take the specific example that we've used in a previous video, where, for example, this could be, we take a specific example just so we can put some numbers in. We can take aluminum as our electrode material and the aluminum cation as the electrolyte. That's for the anode. And then for the cathode, we can have iron solid in equilibrium with iron 2 plus aqueous. So if we take those specific materials and we let the electrodes be 25 centimeters apart, then we can do a quick calculation. We can see that the change in potential energy, we can't see it yet, but we know from previous videos and discussions that the change in potential energy is the change in voltage times by the test particle here, the electron, or remember we said earlier that the change in voltage was the change in potential per unit charge. So therefore, multiplying both sides by the unit charge, the change in potential energy is the change in voltage multiplied by the unit charge. And if we take these materials as the electrodes, we know that the change in voltage is positive, and it's actually plus 1.22 volts. So let's say it's plus 1.22 volts. This calculation is in a previous video. And then we multiply that by the electric charge. Let's just look at one electron. Now obviously if we had these materials in a beaker, there'd be a lot more than one electron flowing. Let's just say per unit charge, and then we could always scale up by however large the sample size is. So the charge on our test charge here is the electron. Its charge is negative because it's negatively charged. 1.602 by 10 to the negative 19 joules. So we multiply this number by this voltage and we get a negative number because we have a positive multiplied by a negative. So we get a negative number, and that's 1.95 by 10 to the negative 19. The unit of charge is coulomb. The unit of charge is not joule, the unit of charge is coulomb. So we get coulomb volts, and a coulomb volt is also known as a joule. So we can say negative so many coulomb volts or negative a small number of joules, which makes sense because you'd expect joule, the unit of energy, to be the unit of an energy change. Importantly, we can see that the change in potential energy in a voltaic cell is a negative value. So that's what's really important. The change in potential energy here is a negative value. If we were to draw a quick diagram to represent this change, we could plot potential energy on the y-axis. We could plot extent of reaction on the x-axis, which essentially is just time, or at least it's proportional to time. You know, how long is the reaction occurring for? It's proportional to time. And we know that the change is negative, so the final value for potential energy must be lower than the initial value for potential energy. So we might want to draw this something like that. And if we had our test particle here at the beginning, which the test particle here is our electron, then we know that the electron with its negative charge is essentially moving down this potential gradient, which is negative, just like like a marble, for example, would roll down a gradient. We've got our test particle moving down this potential gradient. And recall that this is against the direction of the electric field. So recall the electric field is going from the cathode to the anode in a voltaic cell. But the electron, the way we drew it previously, is moving clockwise. So the electron is moving against the electric field. So if the electron is moving downwards here, then the electric field is moving upwards. So I'm going to draw this real quick. So here, if the way I've drawn it, we have our cathode down here, our anode up here, so the flow of the electric field goes from the positive electrode to the negative electrode, and our electron is moving counter to that. So we can clearly see that when the electron, the negatively charged particle, moves in the opposite direction to the electric field, we have a negative change in potential energy, and this is favored without any extraneous forces, and this is why the voltaic cell generates a positive voltage by its own accord. If we now contrast this immediately with an electrolytic cell, we can do something similar. So I'm going to draw a similar diagram where we have essentially the same diagram used in a previous video in this series, where we have two electrodes, and then we have the cathode, which here now is the negative electrode, and the anode, which is the positive electrode. We have the electric field again going from the positive electrode to the negative electrode. And the specific examples will have the same separation. We'll have 25 centimeter separation. The exact chemicals used previously were nickel and nickel 2. So we have nickel solid and nickel 2. These chemicals would generate an electrolytic cell, and copper. So we can have copper solid and copper 2+. So again, these materials would allow us to actually quantify the change in potential energy. So let's do that. Similar to this calculation, let's look at the change in potential energy. So I've got the change in potential energy, which is the change in the voltage multiplied by the unit charge. So if we use our previous calculation of E standard cell for this chemistry, we'd have a negative value because it's electrolytic and it has to have a negative change in voltage, 0.59 volts, multiplied by our unit charge, which in this case is just one electron. Keep it simple, 1.602 by 10 to the negative 19 Coulomb. We have a negative multiplied by a negative, so we get a positive change in potential. So we get a positive value, and it's 9.45 by 10 to the negative 20 Coulomb volts, or joules. A joule is a Coulomb volt. Okay, so here, in contrast with the voltaic cell, we can see that the change in potential energy is positive. If we were to draw a similar diagram to over here, where we can have extent of reaction which again is just proportional to time. Extent of reaction is just proportional to time. I'll just bend that screen down a little bit. And we plot that against potential energy. Then I want to represent a positive potential energy curve. So I could draw something like this, where over time I've got my little test object, which here is an electron. And just as marbles don't naturally roll up positive gradients, electrons don't naturally go up, well, electrons don't naturally follow an increase in potential energy. Things naturally follow a decrease in potential energy. So in order to push, if this were a marble, for example, in order to get the marble up the hill, you would have to artificially move the marble. The marble couldn't be left to its own devices and roll itself. So electrolytic cells require somebody to go in, supply a force to overcome the natural force, keeping the electron where it is. So there's a negative, so essentially there's a positive change in potential energy pushing it that way. There's a negative change in potential energy going the opposite direction. And that's what we have. If we want this to happen, we'd have to provide a voltage. So this is why we said previously that an electrolytic cell is almost like an appliance. It requires some force to make the electrons move within it. Again, if we were to superimpose the electric field here, then we can see that the electric field would be drawn in the analogous way. So we would have the electric field going this way. We've got our positive electrode here, which in this case is the anode. Our negative electrode here, which in this case is the cathode. We can definitely see, if we go back to our earlier cell diagrams, that our electron is moving against the electric field here. But recall from a previous video, our electron is moving in the same direction as the electric field here. So we've got a reversal of the signage of the electrodes. We've got a reversal in the direction of the electron. And we've got a change in the signage of the potential energy from negative for a voltaic cell to positive in an electrolytic cell.